Hi, so welcome back. So in this lecture, we will look at some of the examples of second order linear ordinary differential equations with exponential inputs. Okay, that's the case that we have studied extensively in the last few lectures. Well, one of the unfinished examples was this one, x double prime plus 5x prime plus 6x is equal to e to the power minus 3t. Okay, this is the exponential input. The coefficient of this is 1, which we referred to as capital A in the previous lectures. Of course, x here is a function of time. Okay, and the question was to solve it. Well, the way we solve, again, referring to what we have learned so far, if I want to find out the particular solution of this differential equation, the way the particular solution could be found was, it had different cases depending on what this factor, which we refer to as small a, what this factor was, how this was related to this B and C, this capital B and capital C, which is 5 and 6 in this case. So the question was this factor small a equal to any of the roots of the auxiliary equation of the homogeneous form of this differential equation? The homogeneous form of this differential equation was just with the right hand side being 0. And the auxiliary equation was, just replacing x by m, the variable, but double differentiation with square, differentiation of one time with just m to the power 1, and just 6 here for no differentiation at all. This was the auxiliary equation, which is a quadratic equation in the variable m. And so what are the two roots of this? Of course, this can be factored into m plus 2 and m plus 3 equals 0. So the two roots are m1 being minus 2 and m2 being minus 3. So depending on whether this rate, small a, was equal to any of the roots of the auxiliary equation, we had learnt the formula for the particular solution of this differential equation. And it turns out that it is, this rate minus 3 is equal to one of the roots, only one, not both the roots, in which case we had the case of resonance, which was the third case that we learnt in the previous lecture. In one of the previous lectures. So this rate here is equal to minus 3. So we have to resort to the second case, which is just capital A, which is the factor here, which is 1, divided by, this left-hand side, this polynomial of degree 2 in m, we call that a function g of m. Because this is matched with only one of the roots, you would have the differentiation of this function, only this function, at this small a. Again, you can refer back to the formulas to the lecture where we had developed these formulas. So the differentiation of this function at the point a here, which is minus 3, and you would have t e to the power minus 3t. This e to the power minus 3t, and with a t here, because if you followed, we applied L'Hopital's rule, so there was differentiation of the denominator once, which brought a t down here once. So if differentiation once here would mean that there's a t here once. Differentiation of this here twice would mean there would be a t squared. That's the case of resonance. So for this one, where this is matched with only or equal to only one of the roots, this is the particular solution. And what is this really? If I can work this out, so I have t e to the power minus 3t up here, up in the numerator. Differentiation of g is 2m plus 5, but at minus 3, if you put minus 3 here, you get a minus 6 plus 1, plus 5 is a minus 1. So this is divided by minus 1, which is really minus t e to the power minus 3t. I hope that is clear. So that's the particular solution. But what is the full solution then? What is the general solution, as we refer to as we called it? Well, for that you need the complementary function as well, which we wrote as xh for homogeneous, and obviously that was a function of t as well. That was a linear combination of two solutions of the homogeneous form of this equation. The homogeneous form was just this, 0 with in the right hand side. The two solutions of the homogeneous form of this equation, which is this, were, well, the two roots were m1 and m2, or minus 2 and minus 3. So one solution was e to the power minus 2t with m1, and the other solution was e to the power minus 3t, that's with m2. And the complementary solution was just a linear combination of these two homogeneous solutions. And so therefore the general solution, as we learnt it before, which let's write as xt, that's the objective. We want to find x as a function of t. That's what it means to solve this differential equation. That was xp as a function of t plus xh as a function of t. Well, let's just write that down. This is minus t e to the power minus 3t plus, this is c1 e to the power minus 2t plus c2 e to the power minus 3t. You can combine these two a little bit, take out e to the power minus 3t common. So let's write this one first. So you have c1 e to the power minus 2t plus c2 minus t e to the power minus 3t. That's how the general solution of this differential equation looks like. Okay. So if we referred back to the model, the example where we had this spring, or we had this body suspended from the ceiling by a spring. So what kind of an oscillation? If this x here, this is the x which represented the displacement at any point of time t. So what does the solution tell us about the movement of this body? Well, I mean, if you look at it, if this is the same as this, obviously, if you look at these two terms, which is the homogeneous part of the differential equation, in other words, without any external force, without the system being disturbed by an external influence, in that case, there is overdamping. This is the case of overdamping. You can go back and refer to the lecture where we have done it. You have M1 and M2 both real and they're different, so that's the case of overdamping. So if you pull this body down and you let it go, these are both decaying. Okay, so really if you plot this function, this is a decaying function, this is a decaying function. The function if you draw the graph, it starts off at time t0. If you put t equals 0, you have c1 plus c2. So this is c1 plus c2. Starts off at this point, which is the initial displacement if you pull it. And then this just decays with time. In other words, it just falls with time. So I'm plotting t along the horizontal axis and this function along the vertical axis. So the displacement falls with time. The displacement becomes smaller and smaller and it comes to a standstill. So it is overdamped. It does not oscillate much. It just goes off to a standstill. Okay. What about this function? This is the term that comes into the solution because of the external influence, which is acting in the form of an exponential. What's the graph of this one? Well, this graph is, if you ignore the negative sign, this is really t by e to the power 3t, you can bring the e to the power 3t down. And because this grows much faster than t, this graph is just going to be something like this, okay? It sort of grows a little and then falls. Well, the negative of this, which is what it is, will just be the opposite, okay? So it will be something like that. So if I add this graph with this graph, well, the effect of it will be, it just pulls this graph down a little bit because you have negative numbers here. And then the effect sort of vanishes as you increase time because this graph really is approaching 0 on the y-axis. So the only thing that happens is that this graph gets pulled down a little bit, and you know. So this really will be the graph. This will be the graph of this dotted line will be the graph of the solution. Okay. It sort of gets pulled down a little bit, but still there is overdamping. Nothing really happens, okay? This is the initial, given an initial displacement in some time from then, the body just approaches the 0 displacement position, or it just stops, okay? Because why this happens is because this function, which is the external influence, is also a decaying function. It's not a growing function, it decays with time. So it doesn't have the long-term effect on this body. It has a short effect, but it sort of dies out quickly. Anyway, that's just the analysis of what this differential, what the solution means. Okay, let's try another one. What about this problem? Let's try with x double prime plus 4x prime plus 8x being equal to e to the power minus 2t. That's another decaying function. Okay. What about this? What will be the particular solution? We have to check whether the particular solution, whether this factor, the small a factor here, the decaying rate of the external force, whether this is equal to any of the roots of the homogeneous form of, equal to one of the roots of the auxiliary equation of the homogeneous form of this. So the auxiliary equation is m square plus 4m plus 8 equals 0. What are the roots? Well, m would be, let's apply the standard formula. So you have a minus 4 plus minus b square, which is 16, minus 4 times 8 is 32, divided by 2, and that is minus 4 plus minus, this is, you get a negative 16 underneath the root. So that comes out as I and a 4 divided by 2. So basically you have minus 2 plus minus 2i. So let's say the first solution is minus 2 with a positive 2i, and the second solution, the second root as minus 2 with a negative 2i. Well, of course, this minus 2 is a real number, and the two roots of the auxiliary equation are complex numbers. So obviously, this is never equal to any of them. So therefore, the particular solution of this differential equation will be the first case, which is capital A, or this factor here, which is 1 in this case, divided by, well, just put, this was G, Gm, just put G of A, which is minus 2. And here you have e to the power minus 2t. There will be no t or t square because this g is not differentiated. We are in the first case, again, go back to the video where we have established those cases. So what is that? So let's just put 2, minus 2 instead of here. So you have 1 by, so g of minus 2 is minus 2 squared is 4. Then a plus 4 and a minus 2 is minus 8. And then a plus 8. So that's just 4. Okay, so 4 e to the power minus 2t. Okay. Right. So that's the particular solution. Well, what's the homogeneous or the complementary function? So what are the two solutions of the homogeneous form of this equation? The homogeneous form is, the right hand side is just 0. That's the homogeneous form. So what are the two solutions of the homogeneous form? Well, the first one is, let's write it here, is the decaying term is, the decaying rate is minus. So this is the minus r, as you would remember. So it's going to be minus 2t. This is one of the functions. This is the omega. Again, referring to the notations or the terminologies that we have used in this series. One of them will be cosine. Omega is 2 here, 2t. This will be the first, or I'm just calling it the first solution of this. The other solution will be the same rate of decay with that comes from the real number, or the real part of the imaginary, or of the complex number, and sine the same omega, which is the frequency. So therefore, this will be a linear combination of these two. So e to the power minus 2t, some part of cosine 2t, and some part of sine 2t. So therefore, the general solution, which is the actual solution, okay, the general solution is this plus this. So it's just going to be 1/4 e to the power minus 2t plus this whole thing, e to the power minus 2t, c1 cosine 2t plus c2 sine 2t. And you can take e to the power minus 2t common. So you have e to the power minus 2t. And I'm left with 1/4 plus c1 cosine of 2t plus c2 of sine, c2 into sine 2t. Well, that's the solution. What does this solution interpret? Again, if we go back to our problem of suspending a mass by a spring, again there is a decay here. So the oscillation is going to stop. But before the decay starts, so let's graph this. Let's draw the graph of this function, this solution. When t is 0, I'm again plotting t along the horizontal axis. When t is 0, you have this will be 0 because sine 0 is 0. You will have 1 from cosine 0. So you have c1 plus 1/4. So it's just going to be c1 plus 1/4. That's the starting point. That's the initial displacement when you pull it down. And then without the decay, if it's not decaying, without this term, how is this going to look? Well, this is the oscillating part of it. Okay, that's a wave. But now it's constantly shifted by 1/4. So this is where it is shifted. Okay. And so therefore, this sort of looks like this. Okay. Now we add this decay, or we multiply this decaying term, decaying factor here with this. And then this one is just falling. It just falls. It's a falling function. It's a decaying function. If you product it with this, well, it just brings the whole thing down. Okay. See, what happens is this really is the amplitude. Okay, it's the amplitude. In fact, you can get it from here. It's the amplitude of this wave. Okay, in fact, what we can do is we can draw it from this one. This one has a decaying amplitude, so it's just going to be, it starts off at some point and it's just going to be like this. And this is added by another decaying factor, which sort of looks like this. It starts at 1/4. This is 1/4. So basically, this whole thing is shifted by this function, shifted up by this function. So really, this new function, this new graph of this graph and this graph added is just this thing shifted by this one, and it's just going to be, well, it is shifted by 1/4 up initially, and then the shifting gets smaller and smaller because this function falls. So it's just going to be like that. That's the graph. So if you analyze the movement of this, if you give it an initial movement, it is going to oscillate. But it is going to oscillate, but the oscillation is going to, again, come to a standstill in a manner that is depicted in the graph, okay? It is going to oscillate, it is going to come up with the, suppose this is the initial position before the body has been pulled, so it oscillates like that, and then it sort of comes and stands still at this point after a long while as t reaches infinity. All right. So that's the analysis of the solution of this differential equation. We'll do one last, and let's see where this goes. This is an interesting example where I modify the left-hand side of the previous problem just a little bit. I make this 4x, and I keep the same input as before, exponential input with the same rate of decay. For this, again, let's find out the auxiliary equation for the homogeneous form. Well, that's m plus 2 whole square as a factor on the left hand side. So the two roots are the same. m1 and m2 are both real, and they're same. This is minus 2. So the particular solution of this differential equation will be the third case of, this is the case of resonance, where you would have capital A, which is 1, divided by 2, a double differentiation of this function, a quadratic polynomial of degree 2 in M, double differentiation at the point minus 2. Double differentiation just gives me 2. So that's the 2 here. I will have a t square because I have differentiated this g twice. And I will have e to the power minus 2t. That's the particular solution. What's the homogeneous solution of the homogeneous form of this equation? The homogeneous form is obviously 0 on the right hand side. So the two homogeneous solutions are e to the power minus 2t and t e to the power minus 2t. Well, therefore, the general solution will be first the particular solution, which is half t squared e to the power minus 2t, plus, well, a linear combination of these two solutions, so a c1 times e to the power minus 2t and the c2 part of t e to the power minus 2t. Okay, so e to the power minus 2t is common in all of them, so let's just take that out. It's again the decaying factor, which is common in all the three terms. So you're left with a c1, which is a constant, a c2t, which is a linear term, and a half t squared, that's a degree 2 term. Right, that's the solution. That's the solution for the differential equation. This one. What does this signify? If I have to analyze the movement of, again, the movement of this body, what would this solution signify? Well, now we are back to because we are already in the case of resonance, we are back to more resonance in the sense that when we did not have the input on the right hand side, the solution, if this system is let to function on its own without any influence from outside, or zero interference, zero input on the right hand side, but still in the case of resonance, the solution was some decaying part, which I'm keeping at, some decay, alpha, and m plus nt. Again, refer back to, I'm using the same terminology as before. This is a polynomial of degree 1, it's line. Okay. This was, and we said that this is a product where if the decaying rate is very small, in other words, alpha is very small, this dominates for a while. So the graph of this would be, as long as this is dominating, it would increase because it's an increasing function. Then once the effect of this one kicks in, it falls. So that's how this graph looked like. But for this one, you see now it's more or less like this one, but with another added factor here, half t squared, which makes this polynomial, a degree 2 polynomial, which has more increasing effect. So this is a even more dominating factor than this one. So this increases more than this because it's a degree 2 polynomial. So again, if this decaying rate, if this 2 minus 2 is small, well, small compared to what these constants are, if the constants are big enough and that makes this polynomial dominating for a while, eventually this will dominate because exponential obviously always trumps polynomials so far as growing is concerned. So, but till the time that this is the dominating factor, the graph of this, starting from some point, the initial displacement, it would grow probably more than what this factor, a linear factor would grow, and then it would fall. Okay, it keeps on falling. And so this is again the case of resonance, and it's this factor, which is the external input being matched with being equal to the roots of the auxiliary equation, sort of adds to the resonance. Now, this is the initial displacement, and as I said, if you refer back to the lecture where we talked about resonance, if you give it a pull, initial pull, and then you let it go, the displacement increases. The spring doesn't really bring it up. In fact, the displacement increases more and more, sort of on its own. And then finally, as this factor kicks in, it comes up and it comes to a standstill because the displacement goes to 0. So, therefore, and because of the external factor which is fueling, sort of mixing with the roots of this auxiliary equation, it fuels the extra displacement in the case of resonance and makes the effect of the resonance even more. Okay, so it makes the displacement, initial displacement, which is an abnormal one, more than the initial displacement. It makes that more. So this is the case of, in this case where this factor is equal to both the roots, that gives more resonance. Okay, so this is an interesting example. All right, so I think we've covered more or less the types of examples that can arise with an exponential input. And I think we will take things forward with some other topics in the next lectures. Thank you.